One metal can make steel stronger and help store the energy of the future. This is vanadium, element 23.
What if one relatively obscure metal could make steel stronger and also help store electricity generated by the sun and wind?
That is quite the opening question. I mean, it sounds almost like an alchemist's dream, finding one single material to solve two completely different pillars of modern engineering.
Right, and well, that dream is exactly what we are unpacking today. Welcome to the deep dive.
Yeah.
We are looking at element 23 on the periodic table, vanadium, chemical symbol V.
Yeah, and it's a fascinating one.
It really is. Our mission for you today is to explore our sources and uncover how this incredibly quiet, unassuming element, which, by the way, sits snugly right between titanium and chromium on the periodic table, somehow manages to connect ancient minerals, modern aerospace engineering, and the very future of human energy.
I am so thrilled we are exploring this one today because if you look at the transition metals, vanadium is, well, it's the ultimate dark horse.
The dark horse.
Exactly. It sits in the background, heavily overshadowed by its famous neighbors like iron and titanium. But it is quietly powering the world in ways that dictate the physical limits of our infrastructure.
And like any good dark horse, its origin story is just full of drama. I mean, we're talking about a literal soap opera of science here.
Oh, absolutely. To really understand vanadium, we have to pull back to the early 19th century. So the year is 1801, and we are in Mexico.
Okay, setting the scene.
Right. There's a Spanish-Mexican mineralogist named Andres Manuel del Rio, and he is studying a brown lead-bearing mineral. And as he's studying it, he realizes it contains a completely unknown element.
He actually catches it.
He does. He runs the chemical tests, observes the reactions, and he knows for a fact he has discovered something brand new.
He even gives it a name, right? Based on the fact that its compounds are just incredibly colorful. He calls it erythronium, from the Greek word for red, because, well, it turned red when heated.
Yeah, but then the controversy starts almost immediately after.
Because science is never easy.
Never. The scientific community at the time absolutely refuses to accept his findings. Prominent chemists in Europe look at his work, and they basically dismiss this new element as just being a contaminated form of chromium.
Wow.
Yeah, I mean, to be fair, the transition metals share a lot of similar properties, which makes them notoriously difficult to isolate. So the establishment essentially tells him, you just made a mistake.
Gosh, I mean, have you ever brought a genuinely brilliant, well-researched idea to a meeting and you lay it all out and the room just looks at you and says, no, we're pretty sure that's just the old idea we already had, and they completely dismiss you?
It is exactly that. It's the 19th century scientific equivalent of having your big project shot down by the board of directors. Del Rio literally isolated element 23, and the consensus effectively erased his discovery from scientific history for decades.
He was entirely right.
He was. But it took nearly 30 years for that redemption arc to happen.
Right, so let's fast forward to 1830. A Swedish chemist named Nils Gabriel Säfström is studying iron ores, and he rediscovers the exact same element hiding inside them.
Yeah, Säfström isolates it, verifies that it actually is a distinct element, and, well, he gets the privilege of naming it. And he chooses the name vanadium, inspired by Vanadis.
Which is another name for the Norse goddess Freyja.
Right, the Norse goddess associated with beauty and fertility.
And see, this is what caught my eye. We are talking about a hard industrial metal found deep inside iron ore. Naming a heavy metal after the ancient goddess of beauty feels like, I don't know, a massive leap.
It does sound weird at first, but you have to look at its chemical signature. Vanadium possesses this remarkable ability to produce compounds with exceptionally vivid, striking colors.
Hence the beauty connection.
Exactly. When Säfström and other chemists were dissolving it in acids, they weren't just seeing dull gray powders, they were observing this vibrant spectrum. Depending on how they treated it, the solutions would turn lilac, green, blue, or yellow.
That is wild. And those colors are actually the first visual clue to vanadium's invisible chemical structure. We're looking at what chemists call a chameleon element.
A chameleon element, yes. The changing colors are a direct physical byproduct of its shifting oxidation states. If we transition from what vanadium looks like in a beaker to how it behaves on a molecular level, it gets incredibly dynamic.
Let's visualize those oxidation states for the listener. Because, oxidation state can sound like abstract textbook jargon, but it's really just a measure of how many electrons an atom has shed or absorbed.
That's a great way to put it. A lot of elements are, well, highly rigid. They have one or two ways they like to arrange their outer electrons, and they lock into those configurations.
They like their routines.
Right. But vanadium is situated in the D block of the periodic table, meaning it has a complex outer shell of electrons that it can easily part with. It can comfortably exist in 4 different stable oxidation states.
4 of them.
Yeah, it can give up 2, 3, 4, or 5 electrons and remain perfectly stable.
You can think of it like a highly advanced Swiss Army knife, but on a molecular level. It's not just having different tools, it's that the metal physically reconfigures its magnetic and chemical properties in real time, depending on its environment.
Exactly. By shedding or absorbing those electrons, it adapts to bond with a huge variety of other elements.
Which is huge for us.
Oh, massive. That flexibility makes it incredibly valuable for modern engineering. The most immediate place we see this adaptation applied is in materials science, specifically the creation of highly specialized steel.
Right, the sources single out vanadium as the absolute secret ingredient in aerospace and infrastructure steel.
Yeah, because when you're engineering critical infrastructure like a massive suspension bridge or the internal frame of a modern aircraft or a jet engine, the material has to survive enormous continuous physical forces without warping.
And it cannot be too thick, right?
Yeah.
Or the resulting weight just makes the design impossible.
Exactly. We can't build airplanes out of solid, foot-thick iron blocks. They would never get off the ground.
Right, so we add vanadium to the mix.
Yep. By alloying just a tiny fraction of vanadium, often less than 1% into the molten steel, you fundamentally alter the steel's microscopic architecture.
Okay, wait, how does that actually work? Because my brain immediately goes to comic books. I hear super steel, and I picture some indestructible sci-fi metal like vibranium. Let's manage our expectations and explain the actual mechanism.
I love the vibranium comparison, but yeah, we need to ground this. Vanadium steel will still dent in a car crash. It is not magic.
Good to know.
The transformation happens at the grain level of the metal. See, when normal steel cools, it forms microscopic crystals, or grains. If those grains are large, the steel is weaker and more prone to bending or cracking under stress.
Okay, so the vanadium basically acts as a microscopic anchor.
That is exactly it. That chameleon chemistry we discussed allows the vanadium atoms to bond intensely with carbon and nitrogen inside the steel. They form these incredibly hard microscopic compounds called precipitates.
Yeah, precipitates, right. Yeah.
And these precipitates essentially lock the grains of the steel in place, preventing them from growing too large while the metal cools. And then they stop those grains from sliding past each other when the steel is put under pressure later on.
It's basically pinning the internal structure together, so you get peak engineering efficiency. The steel achieves massive resistance to wear, heat, and structural fatigue without adding significant weight.
Which is why you see the specialization applied everywhere. In high-strength tools that cut through other metals at high speeds, in automotive axles and engine components that handle millions of tiny explosions in extreme heat without warping.
Okay, so if vanadium is that good at shifting its oxidation states, I mean, if it can dynamically juggle its electrons to lock steel together, could that exact same chemical trick solve an entirely different modern problem?
Oh, you are reading my mind. That flexibility leads us directly into the most cutting-edge application of element 23 today, shifting from solid metals to liquid energy.
Which brings me to the million-dollar transition question we have to ask. What happens when solar panels stop producing electricity at night, or when the wind stops blowing?
And that right there is the core dilemma of the global energy transition. We are building massive solar farms and erecting forests of wind turbines. But generating power is only half the equation.
Right, because you have to use electricity the exact millisecond it is generated, unless you can somehow capture and hold it.
Exactly. If we want a reliable grid powered by intermittent renewables, we need massive, unprecedented levels of storage. The energy from the midday sun has to be saved for the evening peak, when millions of people turn on their lights and appliances.
Enter the Vanadium Redox Flow Battery, the VRFB.
Yes, the flow battery, which is completely different from what most people imagine.
Right. If you picture the lithium-ion battery inside your smartphone or electric car, it is a sealed, solid box. Everything required to store the energy is packed tightly into one static container. The flow battery completely upends that architecture.
It does. You really have to erase the image of a solid battery entirely. A vanadium redox flow battery stores its energy in 2 separate liquid electrolytes.
Oh, liquids.
Yeah, and these liquids are not kept inside the battery cell itself. They're held in massive external tanks.
Wait, so the actual energy storage medium is just sitting in vats of liquid outside the system?
Exactly. When you need to charge the system, say when the sun is hitting your solar panels, you pump these two liquids from their tanks into a central electrochemical cell.
Okay, so they move.
Right. The electricity from the panels flows into the liquids, charging them up, and then they are pumped back into their respective tanks to sit there until the grid needs power.
Oh, and the vanadium ions are dissolved directly into that liquid.
Yes. And this brings us right back to the chameleon element. During the charging and discharging process, as those liquids flow through the central cell, the vanadium ions literally change their oxidation states.
Oh, wow. So one tank has vanadium ions that have shed a certain number of electrons, and the other tank has vanadium ions in a completely different state.
You've got it. As electrons move through the system, entering from a solar panel or leaving to power a city, the vanadium flawlessly catches and releases those electrons.
It's juggling them again.
It's just juggling them. On one side of the battery, the vanadium cycles between being missing 4 electrons and missing 5. On the other side, it cycles between missing 2 and missing 3.
Wait, if it is the exact same element on both sides of the battery, just existing in different oxidation states, that solves a huge problem with liquid batteries, doesn't it?
Yeah.
If the membrane separating the liquids ever leaks and the two sides mix, they don't permanently contaminate each other.
That is a brilliant observation. Cross-contamination is a massive degradation issue in other battery chemistries. But with a VRFB, if the liquids mix, you just have mixed vanadium.
No harm done.
None. You can literally just reapply an electric current to sort the oxidation states back out, and the battery is as good as new. The liquid electrolyte effectively never degrades.
That structural longevity is incredible. But the architecture also implies something huge for scaling. If the power generation in the central cell is completely decoupled from the liquid storage tanks, capacity is just dictated by the size of the plumbing, right?
Yes, the scalability is the defining advantage of the flow battery. If you want to store more energy, meaning you want the battery to supply power for 12 hours instead of 4, you do not need to build more central battery cells.
You just construct larger liquid tanks and pump in more vanadium electrolyte.
You just make the vat bigger.
That's amazing.
And if you need more power output, meaning you need to release a massive surge of electricity all at once to meet a sudden spike in city demand, you don't touch the tanks. You just increase the size of the central electrochemical cell where the liquids interact.
This dynamic makes them ideal for grid-level long-duration storage, taking an entire daytime's worth of solar farm energy and saving it to run a city all night.
Absolutely perfect for it.
Which forces a challenge to the premise, though. If you can just build bigger tanks, and it neatly solves the renewable energy storage problem by juggling electrons without degrading, why aren't they everywhere? Why isn't every solar farm flanked by massive tanks of vanadium?
It's a fair question. And while flow batteries are a brilliant piece of engineering, they are not a universal silver bullet solution to all our energy woes. Our sources highlight some strict physical and economic limitations.
The first being the footprint, I imagine.
Right. The physical size is immense. The energy density of the vanadium liquid is relatively low compared to, say, the tightly packed solid lithium-ion batteries. You need huge volumes of liquid to store the same amount of power.
So those giant external tanks take up a tremendous amount of physical space.
Exactly. You could never put a flow battery in an electric car. It would be the size of a moving van. They're strictly for stationary grid-level installations.
That makes sense. And the second limitation has to be tied to the supply chain of the element itself, right? Because vanadium is a specialized metal heavily tied up in the steel industry.
Yes. Gathering, extracting, and processing vanadium to the extreme chemical purity required for these liquid electrolytes is expensive and difficult.
So it's a cost issue.
A huge one. The upfront capital cost of filling massive industrial tanks with highly purified element 23 is a significant economic hurdle that has definitely slowed widespread adoption.
Okay, so it is a brilliant piece of the renewable energy puzzle, specifically suited for stationary infrastructure where physical space isn't an issue.
Exactly.
It's fascinating to think about giant tanks of this ancient chameleon metal sitting out in the desert next to a solar array, quietly absorbing the sun's energy by shifting its electrons.
It really is. But, we think we are so clever engineering these giant vats of vanadium to manage our energy grid. Biology actually beat us to it by a few 100 million years.
Oh, yes. The biological side of our source material is wild because vanadium is naturally present in the environment around us. Trace amounts of it are in the soil, and it enters our bodies through the food we eat and the water we drink.
Yeah, it is ubiquitous in tiny trace amounts. But the true marine mystery scientists have been studying for decades revolves around sea squirts, scientifically known as tunicates.
These were simple, filter-feeding marine organisms clinging to rocks on the ocean floor, right?
That's them. And these organisms actively accumulate vanadium from seawater to extraordinary concentrations. We are talking about concentrating it millions of times higher than the surrounding ocean water.
Millions of times. How are they physically doing that?
They possess these highly specialized binding proteins called vanabins. And these proteins actively seek out vanadium ions in the water and lock them into the organism's biological system, storing them in specialized blood cells.
Okay, but why do they hoard it? Are they using it to carry oxygen the way human blood uses iron?
Well, that was the initial scientific assumption, but it turns out vanadium is actually a terrible oxygen carrier compared to iron.
Oh, really?
Yeah. The prevailing theory now is that they might use it as a highly toxic defense mechanism against predators, or it plays some localized role in their cellular metabolism that we just still don't fully understand.
Okay, knowing that vanadium makes steel super strong, powers advanced batteries, and that marine animals are hoarding it, it immediately prompts the modern wellness question for me. Should I be buying vanadium supplements to optimize my biological systems?
Oh, I need to strongly caution against that.
So no vanadium pills with breakfast.
Definitely not. Unlike elements such as iron or calcium, which your body explicitly requires to build red blood cells and bone density, vanadium is not currently recognized as an essential human nutrient.
Meaning our biology has not evolved a requirement for it to function.
Exactly. Furthermore, exposure to high levels of certain vanadium compounds is actually hazardous to humans. The marine organisms that accumulate it evolved highly specialized sequestered pathways to handle the heavy metal. We do not possess those pathways.
That makes a lot of sense. And I think the larger lesson here is vital for anyone listening, especially when navigating today's landscape of health claims, chemical fears, and technological hype. Chemistry is entirely dictated by balance. The old adage stands, the dose makes the poison.
Oh, absolutely. Context, chemical form, the specific environment, and the dose fundamentally dictate how any element interacts with the world. Vanadium is basically the ultimate case study in context.
In a steel alloy, it provides life-saving structural integrity to a jet engine by pinning the microscopic grains of metal together. In a controlled flow battery, it provides sustainable energy by cleanly passing electrons back and forth. But in the human body, in the wrong chemical form or at too high a dose, it is a metabolic hazard.
Right, you just cannot decouple an element from its context. It strips away the binary idea that elements are inherently good or bad. They are simply tools governed by the laws of physics. The metal of transformation requires us to be incredibly precise about how we apply that transformation.
Well said. Zooming out to look at the entire journey of element 23, it is a profound narrative. We began with a disputed, frustrating discovery in 1801 Mexico, where a brilliant scientist was told his colorful rocks were just the mistaken form of chromium.
A discovery that disappeared into the scientific ether for 30 years.
Right. Then it is resurrected, named after the Norse goddess of beauty because of its vibrant shifting chemistry. It is revealed to be a molecular chameleon, shedding and absorbing electrons in a way that makes it the secret anchor in aerospace steel, keeping our bridges standing and our infrastructure secure.
And today, it is taking the form of a liquid battery that could store the renewable energy of tomorrow.
It possesses an immense resume for an obscure transition metal.
It really does. And it leaves me with a final, provocative thought regarding the future of our civilization.
What are you pondering?
It's just fascinating how the most famous elements always command the historical spotlight. Gold drove entire empires and economies. Iron secured entire historical ages named in its honor. Titanium is the universal cultural buzzword for strength.
True, they get all the glory.
But as humanity moves toward a highly precarious, renewable energy future where our climate and the stability of our global grid are on the line, well, our actual survival might not depend on those famous metals. It might rely entirely on these lesser-known background elements.
The ones quietly hiding in the dark.
Exactly. Gracefully moving electrons, holding the infrastructure together.
The quiet ones doing the heavy lifting while the famous metals take the credit. Which brings us right back to where we started our deep dive today. What if one relatively obscure metal could make steel stronger and also help store electricity generated by the sun and wind? Now you know, it's element 23, it's vanadium. Follow atomic 118 for the next element, and like this episode if you enjoyed the journey through the periodic table.
And you'll definitely want to join us for the next one. The element sitting right next door has its own wild history, and it is waiting to be uncovered.